Hello, welcome to Chemistry Travels. So, in part 1 of Modern Periodic Table, we learned about how we can classify the 118 elements that we know into several groups, periods, and all. And now, in part 2, we are going to look into certain trends that are shown by these elements when they are arranged in a periodic fashion. The first one is atomic radius. How does the atomic radius of elements vary as we move from left to right of a periodic table and from top to bottom of the periodic table? That is how it varies within a group and within a period. Atomic radius. To talk of the atomic radius of an atom, it is not possible to exactly know the size of radius of an atom because the electrons in the atom, they are not having any fixed position. You can't really predict the position of an electron. It's only the probability of finding an electron around the nucleus that can be found out. So another way, a way to find out the atomic radius is consider two atoms of the same element that are touching each other, and then if you draw a line between these centers of the two atoms, that distance between the centers of two atoms of an element that are touching each other, you take the distance and half it. Half of that distance between the centers of the two atoms of an element that touch each other would be equal to the atomic radius, which is generally represented in picometers or nanometers and all. Okay. And how does this atomic radius vary? So along a period, if you move from left to right of the periodic table, we can find that this atomic radius decreases. But if you move from top to bottom, that is within a group, the atomic radius increases. Okay, why does it decrease? Because when you keep going from left to right, what is happening? You are adding an extra electron to the same shell. The energy level is the same. N equal to 1 means you are adding to the first shell only. You're not adding to the second shell, right? When you go to the second period, N equal to 2. So you're adding to the second shell only. You're not going to the third shell. Same shell, extra electrons are being added, as you can see in the picture here. The second shell has 1 electron. Outermost shell has 1 electron. Here the same outermost shell has 2 electrons. Here the same outermost shell has 3 electrons. So as we move from left to right, electrons are being added to the same shell, and also at the same time you can see that as atomic number increases, the nuclear charge is also increasing. So when you move from left to right, the nuclear charge of the nucleus is increasing, and when extra electrons are being added, as nuclear charge increases, these electrons experience a greater pull towards the nucleus. The effective nuclear charge becomes higher as we move from left to right. So the added electrons experience a greater pull towards the nucleus and hence shrinking the size of the atom. That is why the size is decreasing. But what happens when you move from top to bottom within a group? What happens is when you move from top to bottom of a group, the outermost shell also increases. Then this is like the first shell. Then the next element, the outermost electron of the next element would be in the second shell. The outermost electron of the next element would be in the third shell. So this shells are also increasing. So what happens? The electrons, the newly added electrons, are going farther away from this nucleus, right? They are farther away from the nucleus, so the nuclear pull would not be that strong. Because of this extra shells that are being added up, these electrons experience lesser pull from the nucleus, so their size also increases. Okay, clear. Next property is the ionic radius. So the trend shown by the ionic radius is same as that of the atomic radius. That is, it decreases along a period, increases along a group. Okay, that is there. But if you consider an ion of a particular atom, we'll have a parent atom and we can have a cation out of it, and there can be an anion also. Okay, right. So if you consider it that way, the cations are generally smaller in size compared to the parent atom, while the anions of the parent atom are larger in size. Why is that? Because in cations, the number of electrons become less. The cations are formed by the loss of an electron. Right? If I consider calcium as a parent atom, Ca2 plus, the cation, is formed by removal of 2 electrons. So nuclear charge remains the same even though the electrons are going out. The nuclear charge of calcium or whatever parent atom it may be, it remains the same. Nuclear charge remains the same, but the number of electrons have reduced. Because of that, the existing electrons will experience greater nuclear charge earlier if that particular nuclear charge, some quantity x, was shared between 10 electrons, means now 2 electrons have gone out and only now 8 electrons will share that existing x nuclear charge, right? So nuclear pull of other electrons increases, and that is when the size shrinks. But if you consider the case of anions, now nuclear charge remains the same as that of the parent atom, but the number of electrons increases. Anions are formed by gain of electrons, like 1 or 2 electrons are gained. At that time, what happens? The nuclear charge remains the same. Now this whatever quantity of nuclear charge we have, that has to be shared between the existing electron as well as the newly added electron. So number of electrons have increased. So individual electrons will now receive a lesser nuclear charge compared to the parent atom, right? And that is why they have a bigger size. Also, there is electron-electron repulsion. Nucleus is not holding them closer. Also, electrons are negatively charged, and when you keep adding more and more electrons to the existing electrons that are existing, they can repel the ones that are coming new. So electronic repulsion also happens. Nuclear pull also reduces, so their size increases here. And when we talk about the concept of ionic radius, we have a concept called isoelectronic species, which are atoms or ions having the same number of electrons. Certain atoms and certain ions will have the same number of electrons, like the case of O2 minus, F minus, Na plus, Mg2 plus. All of them, if you look, will have 10 electrons, right? Sodium is 11, so Na plus will have a loss of 1 electron, so it is 10 electrons. Mg is 12, magnesium is 12, has 12 electrons, but plus 2 means it will also have 10. Fluorine is 9, so it has a gain of 1 electron, F minus, which means that also has 10. Oxygen also from 8, it gains 2 more electrons to form O2 minus, so total 10 electrons. So all of these species, they are different elements with different charges, but they have the same number of electrons. They are isoelectronic species. And these isoelectronic species also, if you look into the example, you can see that all of them have different nuclear charge. One has 2 minus, another has minus 1, then sodium has a plus 1 charge, magnesium has plus 2 charge. So the nuclear charges are different. So that radius, the pull of the electron would also be different, and hence their radii would be different. And you can see that if the positive charge is more, like Mg2 plus and Na plus, so 2 plus is more. If the positive charge is more, it means that radius will be smaller. More the positive charge means more the nuclear charge, so greater will be the pull of the electron, so radius will decrease. But if you consider the negative charge, greater the negative charge, like 2 minus if you consider and minus 1 if you consider, definitely the one with 2 minus will have a larger radius, because it means that more number of electrons are added. So repulsion between the electrons would be more and nuclear pull would be less. So in that case, the radius will increase. Okay, this is about isoelectronic species. Next is the ionization energy, the trend that is shown in case of ionization energy. So ionization energy, as we know, is the energy that is required to completely remove an electron from a gaseous atom or ion in its ground state. Okay, and this ionization energy, it's an energy that is required. So energy required is always positive value. Okay, and you have several things like the first ionization energy, second ionization energy, third ionization energy, and so on. And first ionization energy means the energy that is required to remove the first valence electron, one valence electron from a metal or from a atom. Like you have M, which is an element or an atom. If you are removing one electron from its outermost shell, or valence electron, if you're removing, it becomes M plus. And giving out some energy is needed for that. That is the first ionization energy. And if you're removing one more electron, that is the energy that is required to remove a second valence electron, that would be the second ionization energy. So here, now instead of a neutral atom, now it becomes a charged atom that is undergoing a further reaction, a further removal of electron. And then we have the third ionization energy, which means that energy that is required to remove an electron from the third valence shell. And if you look into the order of these energies, we can see that the third ionization energy is larger compared to the second, which is much larger compared to the first ionization energy, because removing an electron from a neutral atom is much more easier compared to removing an electron from their charged species. Okay, clear. Now, how does this vary the element? What is the trend shown in case of ionization energy? Along a period, that is when you move from left to right of the periodic table, you can see that the ionization energy of elements increases, but if you move within a group, that is from top to bottom, we can see that ionization energy decreases. And what are the reasons for this increase or decrease in ionization energy? The first thing is the size. So if the size of the atom is larger, it means that when you have a larger sized atom, it can mean that the outermost electron is much farther away from the nucleus. They do not have that much of attraction towards the nucleus, so the electron can be easily removed off. Another property is the nuclear charge. So if you have a greater nuclear charge, it means that the electrons and the nucleus have a greater force of attraction. So the electrons are held closer towards the nucleus. They are attracted strongly towards the nucleus. So if they are strongly held, greater nuclear charge, then you will need more energy to remove an electron. Electrons and nucleus are strongly held because of strong nuclear charge. So you will need more of an energy to remove an electron. So ionization energy also automatically increases. The next one is the screening or the shielding effect. That is, when you have these inner electrons that will shield or cover the outer electrons from the nuclear pull. The nucleus has the ability to pull all the electrons towards itself because of its positive charge and the negative charge of the electron. A force of attraction exists between nucleus and the electrons. Now, we have the inner electrons, we have the outer electrons, and these inner electrons has the ability to screen or shield the outer electrons from the nuclear pull. And now, if the more number of electrons are there in the inner shells, they will screen the outer electrons more strongly from the nuclear pull, so the outer electrons can be easily removed off. That is, greater the screening effect, greater will be the energy that is, greater the screening effect means lesser will be the energy that is needed to remove the electron. That is, if they are screened from the nuclear pull, then you can easily remove them off. Greater the shielding effect, lesser is the ionization energy. Okay. Then we have penetration effect. Depending on where the electron is present, the outermost electron is present, we can we can say that subshells have some penetration effect where s orbitals, s subshells have the greatest penetration effect, followed by electrons in the p subshell, followed by d subshell, and finally the f subshell. Electrons in the f subshell will have the least penetration effect, so they can be easily removed off. And the electrons in the s subshell, they will have, if your outermost electron is in the s subshell, it means that that electron is strongly held to the nucleus. The penetration effect is more, so you will need higher energy to remove an electron. So ionization energy also automatically increases. Okay. And finally, the electronic configuration. So if you look into the configuration of all the elements, you will see that certain elements have half-filled or fully filled orbitals. And that is a reason for a greater ionization energy for those elements. Half-filled and fully filled orbitals are stable, so you will need a very high energy to remove an electron because you're going to make them unstable. Like the case of this, if you consider the noble gases, they have the stable electronic configuration. Their outer orbitals or octet is formed, 8 electrons in their outer shell, and it will be very difficult to remove an electron from the noble gases. That's why they are inert. And also, if you consider the properties, you can see that beryllium and boron, if you consider and all, beryllium will have a higher what we say ionization energy. Nitrogen has a higher, magnesium, phosphorus. If you look into these, there are exceptions and they have a higher ionization energy because of their stable configuration. Okay, clear. Next trend is electron gain enthalpy, which is the enthalpy change that occurs from the addition of an electron to a gaseous atom. If you add an extra electron to the gaseous atom, the energy change that occurs, that is the electron gain enthalpy. It can either be positive or negative. That is, sometimes energy is needed to add an electron, or sometimes energy is released when you add an electron. Based on this, the reaction can either be endothermic or exothermic. Okay, how does that vary? As you move from left to right along a period, you can see that electron gain enthalpy becomes more and more negative. Okay, and the group 18 elements, as we saw, they are the noble gases or the inert gases. So they have a positive electron gain enthalpy because so much of they can't take up an extra electron, right? Like the way how they can't lose an electron, they can't take up an electron also. They're already in their stable configuration. So much of energy would be needed for this. So their electron gain enthalpy is highly positive. But otherwise, starting from left to right, the electron gain enthalpy becomes more and more negative up to halogens. And if you move within a group, that is from top to bottom, we can see that the electron gain enthalpy becomes less and less negative. Okay. And now, if you look into the electron gain enthalpy of oxygen or fluorine, you can see that it is less negative than their succeeding elements like sulfur or chlorine. Why does that happen? Oxygen and fluorine, if you consider, the added electron is going to the n equal to 2 quantum level, right? So it's smaller in size. N equal to 2 quantum level is smaller in size, and the electron is going to be added to the n equal to 2 smaller quantum level. So repulsion between the other within the level between the other electrons would be higher. But if you consider the case of sulfur and chlorine, the added electron is going to n equal to 3 quantum level, and here it's a bigger one. N equal to 3 quantum level has larger space, so the electron-electron repulsion would be lesser, and that is why they have a higher electronegativity, electron gain enthalpy compared to the previous oxygen or fluorine, and this is an exception of the trend that is generally shown here. Next is the electronegativity, which is the tendency to attract electrons towards itself. And because of this electronegativity that we have several compounds that are being formed, right? Some particular atoms can attract electrons towards itself, and some atoms repel these electrons. So based on electronegativity, we can say that the electronegativity of an element increases when we move from left to right along a period, and it decreases if we move from top to bottom along a group. And you can relate this to the atomic size. Like smaller the size means more will be the attraction of between the electron and the nuclear charge, right? More the outer electrons will experience more nuclear pull. As we move from left to right, we already saw that the electrons will the extra electrons that are being added, they will experience greater pull towards the nucleus, so they will be strongly held. So that means that they become more electronegative. That is why halogens and all are highly electronegative. Okay, clear. The next one is their oxidation state, which actually represent the number of electrons that can be gained, lost, or shared to form compounds. In simple terms, we can consider it like that. It is actually charged, and you can consider it as the number of electrons that that a particular element can gain, lose, or share and form several compounds. This oxidation state is important in forming several compounds. And group 1 elements are found to show +1 oxidation to state. Group 2 has +2 oxidation state. Then from 3 to 12, they show mixed oxidation states. Transition elements, they show mixed oxidation state, like +1, +2, +3, +4, +5, +6, and +7, all of them. And several elements show different number of oxidation states. Then group 13 generally have +3. Group 14, carbon group family, has +4. Nitrogen family has -3, but it exists in other oxidation states like +3, +5 and all, but most common is -3. Like in the case of ammonia and all formation, NH3, nitrogen will be in the +3 state, right? And then there is oxygen, which has -2 oxidation state. Then we have fluorine in -1 oxidation state, and helium, neon, argon, which this set, the noble gases, they have 0 oxidation state. And if you come to the inner transition elements, F-log elements, lanthanoids generally show +3, actinoids show +3 and +4, but this definitely shows other oxidation states like +2, +5 and all are common for these actinoids and lanthanoids. Okay, clear. The next one is the metallic and non-metallic character. We already saw in the initial slides like which of those elements are metals and which are non-metals, metalloids and all. And metallic character, we can say that it decreases along a period and it will increase as we move from top to bottom. And why it happens? Metals, they tend to lose electrons to form cations. We already saw that when we move from left to right, it is difficult to remove an electron. Ionization energy is increasing, right? It is difficult to remove an electron. So we say that they are less metallic as we move from left to right. Removing electron becomes difficult, so they become less metallic. And these metals, they generally form basic oxides. So this group 1 and group 2, they are very good metals, right? They have greater metallic character and they are alkali and alkaline earth. So they are basic in nature and they form basic oxides. And the more the basic the oxide, higher would be their metallic character. So as we move down, they become more and more basic, and so metallic character also increases. Next, non-metallic character, if you consider, from moving from left to right, it increases, and moving from top to bottom, it decreases. So non-metals, in comparison to metals, they gain electrons to form anions. They can easily gain electrons. And we already saw electron gain enthalpy becomes more negative as we move from left to right. So they can gain more of electrons. And so non-metallic character is higher here. So that is why on this p block elements, they were mostly non-metals as we saw earlier, and they form acidic oxides, and more the acidic character, higher would be the non-metallic character. Okay, so the top ones are more acidic, they have higher non-metallic character. As we move down, their non-metallic character decreases. Okay, clear. And finally, we have an anomalous behavior of the second period elements. And if you consider the elements in the second period for each of the groups, you can find that they differ in many aspects compared to the other members in that particular group. Like, for example, if you consider lithium and beryllium, they are the ones that form covalent compounds. But if you consider the ones below, like sodium, below lithium, we have sodium, potassium, and all, or below beryllium, we have magnesium, calcium, and all. So these won't form covalent compounds, they form ionic compounds. But the starting ones of the second period, that is lithium, beryllium, and all, they will be forming covalent compounds. So many such differences are there. The second period elements alone, they will have properties different compared to other elements in their group. And this is because of their smaller size, larger charge to size ratio, as well as a higher electronegativity values. Also, we can see a diagonal relationship, like if you consider the second period elements like lithium, beryllium, boron, carbon, and all. So instead of being more closely related to their succeeding elements like sodium, lithium relating to sodium, or beryllium relating to magnesium and all, they relate diagonally. That is, they show some similar properties diagonally. Lithium would be more related to magnesium, beryllium would be more related to aluminum, boron more related to silicon, and also diagonally they will be related, and that you can understand by the simple property of size itself. See, we saw that when we move from left to right, size is decreasing, but when we move from top to bottom, size is increasing. So lithium has some size. Now when you go to beryllium, size is slightly decreasing, but when you come to magnesium, it's going down, so size increases. So it's like when you move one step here, size decrease, then one step down, size increase. So it's somewhat similar. Now the initial point and the final magnesium would have somewhat similar size values. Okay, so this is how a diagonal relationship can be noted between these elements of the second period and their corresponding elements. Clear? Okay. So that's it for today about the periodic classification of elements or the modern periodic table. I hope you understood the concept. Thank you so much.